Maxwell's equations, a simple introduction to a great discovery. Hi, I'm Ben O'Regan and my channel is 1000 Celsius. I want to give you a simple introduction to one of the greatest discoveries in physics. Why learn about Maxwell's equations? They're not that difficult to understand if you break them down. Maxwell's equations can seem a bit overwhelming if you try to take in too much information at once. But like most things in physics, they can be quite manageable if you break them down into simple steps. This video is going to be a very simple introduction and it won't have any complicated mathematics at all. Another reason is to round out your knowledge of physics. Maxwell's equations really are one of the greatest discoveries in physics and also not very well known. Not many people know about them. It seems students of physics want to skim over Maxwell's equations to get to something cool like quantum mechanics, or something cutting edge like the latest research from the Hadron Collider. Back in 1687, Isaac Newton published his Principia Mathematica, which completely changed physics. What's less well known is there was a similar revolution in physics in 1873 when James Clerk Maxwell published a treatise on electricity and magnetism. His theories were so extremely versatile in explaining every phenomena in electricity and magnetism in a very fundamental way, and were also incredibly useful for enabling the explosion in electrical and electronic technology which occurred in the 20th century. If you want to know about physics, you should have some understanding of Maxwell's equations. The reason to learn about Maxwell's equations is you may appreciate the beauty of the mathematics. Most people don't think of mathematics as being beautiful, but the physicists who study Maxwell's equations will tell you they're a very elegant set of equations. Mathematicians find beauty in simplicity, and Maxwell's equations, fairly short, four fairly short equations, but they can do a lot. They're extremely versatile. Before Maxwell developed his theories, electricity and magnetism looked like magic. A wire with an electric current causes a nearby compass needle to move. But how does the compass needle know? How does it know there's a current in the wire? Maxwell developed the theory that light is a wave. There are generally two ways for energy to travel from one place to another, either as particles or as waves. With particles can carry the energy from one place to another, but with waves, the medium stays still or moves side to side, up and down, but the energy moves from one place to another, but the medium doesn't get carried with it. Maxwell's equations predicted the existence of radio waves. Incredibly, Maxwell predicted the existence of radio waves 22 years before radio waves were successfully transmitted in a laboratory. Maxwell predicted that there were such things as radio waves in 1864, and Heinrich Hertz successfully tested his theory in 1886, confirming that there are indeed such a thing as radio waves. Empty space is not so empty. I'm going to talk about empty space for a while now. It's useful if we're trying to understand physics, in particular electricity and magnetism, that we think about empty space and get an understanding of how empty space works before we try understanding what happens when we put things in it. If you imagine empty space outside the Earth's atmosphere, there's no matter, there's no air, but it's not empty. It's full of electric and magnetic fields. To show you about Maxwell's equations, I've developed this game analog. In a university physics course, the teacher's going to introduce the Maxwell's equations one at a time, and then they'll go into all sorts of detail about the history, how this was discovered, and all sorts of mathematical derivations and implications. And then finally, after 1 or 2 months of this, they'll come to the big reveal where they'll show you how Maxwell's equations give rise to the wave model of light. As this is a simple introduction to Maxwell's equations, I'm going to cut straight to the big reveal, and I'm going to do this using a game analog. Imagine a game. Space is represented by this chessboard, and there are some red pieces and blue pieces. The red pieces represent magnetic fields, and the blue pieces represent electric fields. Rule 1 of this game is that the magnetic field pieces, that is, the red pieces, can only be arranged on black squares. Why do we have this rule? This rule represents the first of Maxwell's equations, which dictates that a magnetic field in space is allowed to have some distributions or some shapes, but not others. So as we can see from this diagram, a magnetic field can have some shapes, and other shapes are just not allowed. In this simple introduction to Maxwell's equations, that's all we need to know about the first rule. Rule 2. Electric field pieces, that is the blue pieces, can be arranged on black squares only. Why do we have this rule? Well, Maxwell's first and second equations are almost identical. Div B equals 0, remember B represents magnetic field. Div E equals 0, E represents electric field. What this means is that any shape the magnetic field can have, the electric field can also have, and any shape the magnetic field is not allowed to have, the electric field is also not allowed to have. Notice blue pieces and red pieces can occupy the same square. The point I'm trying to make here is that magnetic fields and electric fields can occupy the same space. They don't interfere with each other at all. Rule 3. If a magnetic field piece, that is a red piece, is next to a blue piece, move the red piece clockwise around the blue piece 1 square. I should stress that's 1 square. So if a red piece is next to a blue piece, move it 1 square in a clockwise direction around the blue piece. Why this rule? Maxwell's third equation describes how magnetic fields change over time. Notice the magnetic field changes depending only on the shape of the electric field. If you have some knowledge of mathematics, you'll see this dB dt term, will be, if you remember, represents the magnetic field. dB dt is the rate the magnetic field changes over time, and this curl of E is the electric field. Curl of E is some function of the shape of the electric field. So how the magnetic field changes with time depends only on the shape of the electric field, E. Rule 4 says, if an electric field piece, that is a blue piece, is next to a magnetic field piece, that is a red piece, move the blue piece anti-clockwise around the red piece. Should stress that's 1 square anti-clockwise. Why this rule? Maxwell's fourth equation describes how electric fields change over time. Notice that electric fields change depending only on the shape of the magnetic field. If you know something about mathematics, the electric field is represented by the vector E. The E dt is the rate of change of the electric field with respect to time, equals 1 on mu naught epsilon naught curl B. how mu naught and epsilon naught are just constants, and curl B is a function of the shape of the magnetic field. So, therefore, the rate at which the electric field changes depends only on the shape of the magnetic field. Notice how similar the third and the fourth equations are. What this means is the way that the electric field gives rise to a change in the magnetic field, and the way the magnetic field gives rise to a change in the electric field, is very symmetrical. Notice also, this is important, red pieces can't move on their own, and the same applies to blue pieces. If we had a piece on its own, it stays still. How does this relate to electricity and magnetism? No, electric fields cannot change without the presence of a magnetic field, and vice versa. If we have an electric field in space and there's no magnetic field, the rate of change will be zero. Same with a magnetic field. A magnetic field in space, no electric field, its rate of change will be zero also. This shows us how closely related electric fields and magnetic fields are. Notice also how the red pieces and the blue pieces, if there's a red piece beside a blue piece, how they tend to move across the board together. The key concept is a red and a blue piece have to be together to move. This is analogous to what Maxwell predicted about radio waves. Maxwell's equations predict that if you have a magnetic field in space with no electric field, its rate of change will be zero. If you have an electric field in space with no magnetic field, its rate of change is zero as well. But if you have an electric field and a magnetic field together at the same point in space, they will tend to propagate energy through space at the speed of light. This is what Maxwell's equations predict. Let's have a quick recap. What have we learned about Maxwell's equations so far? Well, we learned there's 4 of them. We also learned that the first 2 equations describe how a magnetic field and how an electric field can be arranged in space. This is analogous to the first 2 rules of our game, which tell how the red pieces can be arranged on a chessboard and how the blue pieces can be arranged on a chessboard. The third and fourth equations describe how magnetic fields and how electric fields change with respect to time, and this is analogous to the third and fourth rule of our game, which describes how the red pieces and how the blue pieces can move over time. We learned these equations are highly symmetrical. The equation that describes how magnetic fields can be arranged in space is almost identical to the equation which shows how electric fields can be arranged in space. And we also learned that the equation that shows how magnetic fields change over time is almost the mirror image of the equation that shows how electric fields change over time. And we learned that these equations predict radio waves. Maxwell's equations showed that electric fields and magnetic fields are very closely related. A magnetic field will always have an electric field associated with it, and vice versa, except in the very special case of a static field, where it's possible to have an electric field or magnetic field by itself. Are you feeling inspired? I hope this simple introduction to Maxwell's equations inspires you to learn more about them. Thanks for sticking with me to the end of this talk, and if you've got any questions or comments, or if you like this video or if you didn't like it, then please leave a comment. Thanks for watching.